Yeah, that's a lot. You're around long enough, your story just gets longer and longer as to what you've been up to. Oh, well, thanks. I hope everybody's had a good show here this weekend. It's nice to be back out amongst people and not completely locked down anymore. So Columbus gave us some beautiful springtime weather. Really. Yeah, we've got snow back in Pennsylvania again today, so I've got that to look forward to. So, all right, so I'm going to talk a bit just this afternoon here about some just basic, just kind of basic operating principles with the decorating mirrors. Try to go through some setup procedures, talk about how do you really determine the capacity of your decorating mirror. Let me just advance this here a little bit. Yeah, figuring out how do you determine the capacity of your lyre. What can you do to try and optimize your loading plan? And that's always can get to be a fairly complicated question, especially with decorators that are doing a lot of different types of products and using one lyre to do all of that. And a lot of times, that can make a big difference on ultimately how the lyre is going to perform. What kind of production you can get through there. So that's always you can talk about that for an entire segment. I want to talk about managing startups and shutdown with decorating lyres. I talked to a few folks in here about that yesterday. Just go over some basic recommended maintenance, and then we can have some questions and answers, anything that comes up. Okay, so we'll start off here just talking about lyre capacity. So the decorating lyre process capacity is really determined by the tunnel time, which is regulated by the belt speed on the lyre. The required belt speed is determined by the product dimensions, the desired production speeds, and your loading plan. The belt speed in conjunction with the zonal set points in the lyre confirms the required preheat rates, soaking time or curing time, as well as, when we're dealing with ACL and glass, it determines the annealing, the re-annealing process, and then finally your final cooling rates. Of course, preheat and cooling rates, as well as the curing times, can vary based on the specific ceramic paint or the ink that you're using, as well as the type of product being decorated. So, when you're decorating glass, so you've got a whole other set of circumstances to deal with there, especially if you're decorating, with high temperature paint at, firing at 1150 or 1200 degrees. You've got to not only preheat the glass and the label, you've got to cure the paint, then you've got to re-anneal the glass, and you've got to get it out of the lyre at a reasonable handling temperature. If you're doing a low temperature product, that whole annealing phase goes away, and if you're doing ceramics, then typically the paint is going to determine what your heat up rates are and what your soaking times are, and not so much the actual ceramic item that you're decorating. So I wanted to just show an example on how you go about calculating a belt speed on a decorating lyre. You can, of course, at any given time, you can simply walk out and measure the speed that the belt is running at. But it helps to know ahead of time if you're looking at scheduling a specific product or a group of products, and you've got a set production rate in mind that you need to try and meet. It's good to be able to do that ahead of time, know what kind of belt speed you're going to need to run, know what kind of tunnel time you're going to have, and this can help you, plan for, any any special considerations, or in some cases determine whether or not you can actually decorate a product. So there's a little bit of given information up there. This is pretty straightforward. So just as an example, if you've got a Lear belt width of 120 inches and you're going to decorate a product that's 5 inches in diameter, and your loading pattern is going to be something along the lines of, you know, half-inch spacing between the product, half-inch spacing between the rows, and your proposed decorating speed is 100 pieces per minute. So all you're going to do is take the belt width, you're going to take the product diameter that you have, and you're going to add whatever spacing it is you're going to end up with. Again, we deal in two very, very different production scenarios. We've got the production scenario where, you're decorating 400 Corona bottles a minute, and then you've got the scenario where you're potentially hand loading glass. But regardless, this is the way you're going to go about doing it, and again, this is a way you can kind of plan in advance and see what your tunnel times and things are going to look like in your decorating mirror before you actually get into producing something. So you take your belt width, you take your product diameter, you determine what is your spacing between each piece going to be across the belt. And you simply take that quantity and you divide it by your belt width. So in this case, you're going to be able to get, you're going to be able to get 21 pieces across this 120-inch wide belt. Then all you're going to do is take the proposed speed that you want to decorate at, 100 pieces per minute, divided by 21 pieces across the belt. Now you know roughly how many rows per minute you're going to have. 4.76 rows per minute. You take your rows per minute, 4.76. Once again, you multiply that by the product diameter, and now what kind of spacing you're going to end up with between the rows on your belt. And then you multiply those two numbers, and that gives you a belt speed of 26.2 inches per minute. So once you know what the belt speed is, then you can look at your Lear, you know what your tunnel length is, you can very easily determine, okay, what is my tunnel time going to be based on this particular production scenario. And again, this is a pretty simple one with just a single product. And again, this can be a little bit more challenging when you're, for instance, if you're hand loading 3 or 4 different pieces all on the same Lear belt. But one of those is going to determine the Lear belt speed, and this is really all you need to go through to figure out a tunnel time on your decorating Lear. Any questions about any of that?
Yeah, no bottle weight is, you're not calculating bottle weight?
Yeah, we'll get to that. This is strictly just calculating the tunnel time and belt speed. Yeah. Okay, so again, talking about optimizing a loading plan. You want to allow for as little space or as little open space on the belt as possible. All right. An annealing Lear or a decorating Lear operates most efficiently when the belt is full and you're at a minimum belt speed based on your production input. You want to try to schedule products of similar size, weight, and thickness as much as possible. When loading multiple products, always know which one defines the belt speed and plan additional products accordingly. So, you're going to have one piece. Okay, so if you're running 2 or 3 different pieces at once, you're going to have one that's going to require, the most tunnel time to get your proper decoration, and you can load products with that. just as long as, they only require an equal amount of time or less. Again, that's a simple situation when it's one single product going through the Lear. Corey, you don't, I don't imagine you mix up products much on your belt. You're running all the same white containers in there at any given time. You guys don't really mix things up much, do you?
We have to, so there'll be heavyweight class with lightweight class, but of course we gotta slow it down for the
Yeah.
heavyweight.
Yeah, basically everything slaves off of the heaviest piece
Yeah.
that needs the most downtime. And you can load products with that, but you can't put something in there that needs, that needs more time than what your dominant piece is.
The lightweight class is gonna be fine.
Yeah, yeah. So the other thing that goes along with a loading plan and with belt speed, again, you want to try and maintain the minimum belt speed that you can achieve, because as far as energy usage and performance on the Lear, you're not only heating and cooling the glass in there, but you're also heating and cooling the Lear belt. All right, so without question, the higher the belt speed, the more energy, the more electricity, the more gas your Lear is going to use. So you always want to set your loading plan up so that you've got a minimum belt speed. You're utilizing the whole Lear mat, and not running it with a lot of open space on the belt, because the belt speed has a big impact on the energy usage. So, Corey was mentioning about weight, and I included this as just kind of a general rule of thumb. And this is for glass, and this is for a high temperature decoration, an ACL, a label that's going to need 1150, 1180, 1200 degrees to cure, but just kind of taking you through the basic steps in setting up a decorating curve, and then some correlation as far as glass weight and tunnel time is concerned. So across the top there, you got basically light, medium, and heavyweight products. I'm sure that you decorate products that are heavier than this. This is just kind of an average snapshot here. And what I've got in there for you are rates. So step one there, and we'll just work right down the first column there. So step one is basically you've got to preheat the glass from entrance temperature to your decorating temperature. You can see the heavier the glass gets, the lower that heat up rate is. So lightweight stuff you can heat up at a rate of 60 degrees F per minute. Heavier weight products, you're at the 900 gram range, you're roughly half of that. Your next step down is your curing or your soaking time. For this example, I've got 15 minutes. That's going to vary somewhat based on the product that you're using. From that point, then with glass, then you've got to take it from decorating temperature to annealing temperature, and those are all for all those products. I'm using roughly a 15 degree F per minute rate there, because what we're trying to get to then is step 4, where we're going from annealing to strain point. Now these are the critical rates here for re-annealing the glass. And again, it kind of follows the same suit. The lighter weight ware, you can cool at a higher rate between annealing and strain point, and as you move across, that cooling rate drops down as the weight of the glass goes up. You'll see cooling rates there for once you are below the strain point to the exit temperature, and then down there at the bottom, I've got just typical total tunnel times for the three different ranges of glass weight. So what you can do with that is you can look at your product mix, what you're running. You can go through the simple steps of calculating the belt speed, figuring out your tunnel time, which the tunnel time is just taking the overall length of your leer, taking your belt speed, which is in inches per minute. So if you've got you just convert the length of the leer in feet to inches and just divide it by the speed of the belt, and that gives you your tunnel time. So I don't know how much pre-planning goes into your calculations when you're looking at products and determining what leer you're going to run on, or whether or not you can actually decorate it. But this can help you through that process a little bit.
John, we were talking
yeah.
strain point, like the quartz inversion temperature.
Yeah. So again, this is based on soda lime glass. So typically the strain point for soda lime glass is going to be somewhere around 890, 900 degrees, somewhere in that range. So that annealing temperature to strain point, that's step 4. So typically the annealing temperature is around 1,020 degrees, and you're going to want to maintain those cooling rates until you get an indicated air temperature in the zone. Typically I work to about 890 degrees F, because then the glass is below the strain point, and then you can move to your next step, or your increased cooling rate from strain point to exit temperature. And I guess that's another point to make for everybody that I do still sometimes have conversations with different decorators, that if you are working with soda lime glass, and if you are firing it at those high temperatures, you are determining the final grade of annealing, or the amount of thermal stress that's in the glass. So whatever it showed up with from your producer, or from wherever you're buying the glass, you are changing that. So if it's well annealed glass when it comes in, it can leave your plant well annealed glass, or it can leave your plant poorly annealed. So that is something that when you're working again with glass, that you need to check. I do a lot of that for decorators. They send me glass and I check the annealing on it. I don't know, some of you may have your own equipment to do that. You've got a fluoroscope and strain discs. You can grade the annealing, but I do that for several decorators. If they've got something that they're concerned about or is in question, they send it to me and I grade it for them. Any other questions on it? Yeah.
Is there any data on the caloric consumption? I know this really depends on the type of glass that you're running and stuff in the leer, but is there like a window of how much caloric consumption that a leer will consume on a per hour basis operating at a specific temperature?
Just usage?
Yeah.
Yeah, so we can calculate you an estimate, but it has to be based on a given set of conditions. So it's based on your specific leer configuration, the product you're running, everything we just talked about here, belt speed, set points, all the information on the glass, the weight of the glass. We can do that, but it is literally all over the map, and it's totally dependent on the production conditions. Most of the time, especially with gas-fired leers, you have, say, as far as available burner output, you most of the time have a lot of excess capacity, especially with gas-fired leers. So it's not all that common to be in a situation where, you know, a decorator's running a product and they call me and they say, well, we can't make second light because we don't have enough BTU. Normally, you've got excess capacity with a gas fire. Now, with an electric heated Lear, that's a whole different ballgame. It's very difficult to get excess heating capacity with any electric Lear because you just don't have enough room to get enough element in there to pass the air by to get, you know, to get a higher BTU value. Most of the decorating Lears, if they're Bowman's or really with anybody, you've probably got close to 1 million BTU per zone available to you with a gas fire Lear. With a decorating Lear, it's going to be much less. So the whole setup and loading and making sure your load plan is correct. Keep hitting this button, sorry. That's what you're doing, you wave your arms around when you talk. This loading plan becomes very important again because you want to keep that belt speed down to a minimum. So it's a little fuzzy with decorating Lears, but with annealing Lears, the biggest energy user is the Lear belt. It's not the glass. Because with an annealing Lear, we're getting glass in the front of the Lear at 900 degrees. So, if everything is running well, you can have an annealing Lear that will occasionally run on zero energy input because you're getting all the heat you need with the glass and all you're doing is controlling the cooling rate. Decorating uses a lot more energy because we're coming in at room temperature, so we've got to keep the glass and belt and all of that. But if you've got a particular situation that you think you're using too much or whatever, if you can contact me and with some input, we can estimate what we think it should be.
What about usage with your exhaust being 100% open to 60% closed?
Yeah. Good. Yeah, that's another big factor specifically with decorating Lears. So most of you, if you're using especially any of the high temperature ceramics, you've got exhaust ducts, and you've likely got some 2 or 3 in front of the Lear to pick up all the volatiles as the paint is initially heating up, and you do get a visible emission that I'm sure is going up some sort of stack assembly. So if those are not looked at and monitored and they're only open enough to get the volatiles out of the Lear, you can most definitely overdraft it, draw heat out of it, and then that will also make your energy usage go up also. That's something that's just you just kind of have to set that based on your experience and getting some knowledge of the product as to how much of a volume of exhaust gases you're getting off of it. I know it varies as far as how much paint's on the container or specifically what kind you're using. But there's a couple of things going on with that exhaust setup. We'll talk a little bit later about just a couple of really important maintenance parts, and one of those is occasionally checking that exhaust ductwork because that material does build up in there and it can catch fire. Okay. Okay, so managing startups and shutdowns. So I know I was talking to a few folks in here yesterday, and just so you all know, any high temperature decorating Lear, be it a Bowman or a Panicam or an Antonini or whoever Lear it is, they are really built to run 24/7 and never shut off. So I know that a lot of smaller volume decorators don't operate in that manner. They're shutting down and starting up, maybe once a week, shutting down on the weekend, or in some cases shutting down and starting up every day. And so that it puts an extreme amount of wear and tear on a Lear, heating it up and cooling it down and heating it up every day. So, again, just some general statements here that, your production planning should result in as little downtime as possible. Keeping the Lear fully loaded and at operating temperature as much as possible. I can tell you that specifically with Bowman Lears, when you get a new Bowman Lear with a manual, it tells you quite specifically in there that the heat up rate from ambient to operating temperature should not exceed 4 degrees F per minute, okay, or about 240 degrees an hour. So, for a typical decorating operation, going from ambient, up to, 1100 plus degree setup, you're looking at, 5.5, 6 hours from ambient to operating temperature. So the reason for that is that, of course, Bowmans are all, we don't use any ceramics inside. Everything is stainless steel. So you get a lot of expansion and contraction when you're heating it up and shutting it down. And if you do that too quickly, you can get, some rapid movement in the ductwork, and you can end up, getting your ductwork up into and making contact with recirculating fan assemblies. You can do a lot of damage in a short period of time. So, you can do it, but you really need to be careful about how quickly the Lear heats up. If at all possible, try not to just go out in the morning and put the set points on the Lear and walk away from it and let it go wide open until it gets there. And I know that happens. And I see some lines going on there. Yeah, it happens. So to get airflow in there, the distance between the actual impeller and the fan plane is quite close. And when you rush that heat up rate, that ductwork will move, and your fan's turning 800 RPM. And, if that ductwork gets up into the fan, I mean, you can, normally you can hear it when it starts to happen. It will sound like a jackhammer or a bad washing machine bouncing around on a floor, and you can arrest the situation. You shut the burners down. There are, Bowman Lears have it, and I think most everybody has it. You've got some adjustments up there where you can move the fans up away from the fan plugs and get them up, stop them from contacting, so you don't. So you can knock a hole in the ductwork, or you can, if you knock a blade off the fan, then you're done. Because you can't run it because it's out of balance, and you're going to have to shut it down and tear it out and put a new impeller in there. So heat up rate is really, you need to watch that. Now, I know nobody's going to take 6 or 8 hours to heat their Lear up, and what you really want to try and minimize is, again, that situation where the burner stands on high fire for 15 minutes or 20 minutes or a half hour until the Lear reaches set point. It's the flame impingement on the ductwork that causes the damage. Your air temperature is only eventually getting up to 1,200 degrees, but you're at 3,000 degrees on the flame temperature there. So you'll see your ductwork turning red. If you look in there, any place the flame's in contact with the ductwork, you'll see it eventually will start to glow red, and then that's when the bad things start to happen. So, if you can't follow the rule to the letter of the law, just try to minimize the amount of time that you have constant burner output and flame impingement. Try to give it a bit of a break. Manually run it down below fire or whatever until you see that color go out of the ductwork, and then let it take off again. But do the best you can there. And of course, shut down. There's a few things to be aware of there when you're shutting down. During shutdown, the recirculating fans in the Lear belt should remain running until the temperature is below 250 degrees. There's a couple little tricks there you can do also. So you shut the burners off. You keep the recirculating fans running, and if you're trying to get heat out of the Lear a little quicker, speed the Lear belt up. All right, so in that case, speeding the Lear belt up will help pull your Lear down a bit faster. If you look to idle the Lear, which is probably the best case scenario, if you've got if you're able to let the Lear run overnight, even though you're not producing glass, you've got somebody in there that can watch it. Idling is definitely the best case scenario. You can literally leave the Lear right on its set point, and close up the doors, close all the exhaust ducts, run the Lear belt speed down to its very lowest setting, and you'd be surprised at how little energy it takes to maintain the set points once you close everything up. And then there's a couple. So maybe you drop it down to 500 or 600 degrees, so you don't have to take as much time to heat it up the next day. Any of that is better than a complete shutdown every day and then a wide open startup in the morning. Because that, like I said, that will seriously decrease the life of almost everything within the heated zones. Ductwork, recirculating fans, skid frames, you can potentially work your skid frames. Avoid that as much as possible. Anybody got any other questions about that?
Yeah, real quick, John, do you have timers for your bowling lanes?
Okay, so there's a couple things available. I'll tell you at the onset. So Bowman does not provide any fully automated startup components. That is a choice that we made, that we do not want to see any Lear that completely starts up from a full stop without there being a human being involved. So we don't supply that. However, you can put set point ramps into your instruments depending on what kind of control systems you have, where it will, you can come in the morning, start the Lear up, turn all the burners on, and you can have set point ramps programmed in the instrument so that it will control on that 240 degrees F per hour for you automatically. You don't have to sit there and keep, trying to up the temperature a little bit every 20 minutes or every half an hour. You can do that with a multitude of standalone just instruments, Honeywell, Eurotherm. They all have set point ramps that you can program. Or if you happen to have a decorating Lear with a PLC, that's a process that is available there, where you can program how quickly the Lear will heat up. There are certain aspects that, yes, we can automate. Certain shutdown systems can be automated on a timer. Basically, we can do anything except a fully auto startup from full shutdown. And that's not because we can't, that's because we choose not to do it.
John, do you have a lot more to go?
I'm sorry?
Do you have a lot more to go?
No, I'm just about,
Take your
just
time.
about finished up. It's important to specifically to get inside and get a look at your ductwork and skid frames and things like that. See if there's anything going on in there. That is something that's a service that we do offer. It's a little bit more of a process than it used to be. We have to treat everything as a confined space now, so the days of me going into a plant and crawling through 5 or 6 layers when nobody was around, and it was no big deal. Can't really do that anymore, so it's a bit more of an issue. The ductwork I mentioned earlier, as much as you can. If you've got inspection ports or doors in your exhaust ductwork, keep an eye on that, because if you get a lot of the volatiles built up on that ductwork, it can and will catch fire under certain conditions. So keep an eye on that, and of course, just do the obvious: follow the procedures in the manuals as you have them, and that's basically all I have.